we are going to just look into some work we have been doing on the role of particle flow interactions with applications for cloud microphysics. So I'll just start with acknowledging the people who have been involved in this work at different stages. So a large part of what I'll talk about today is the work done by my PhD student, Pijush, who recently graduated. The work started out towards the end of my postdoc with Don at Cornell, and the experiments were then being done in collaboration with Greg Voth at Wesleyan. Johnson was then a PhD student who subsequently was in U Chicago, who was also involved at some stages in this work. So to just get things started, when we talk about problems related to atmospheric motion, the first thing that becomes a big hurdle if you are thinking of understanding these problems at either from a simulation perspective or even as a physics perspective is the whole range of scales of motion that are there. So typically when someone says that I'm looking at problems in atmospheric flows and they say it's a small scale phenomena, a small scale phenomena typically would be few kilometers or few hundreds of kilometers. So the language itself is quite different what you mean by small scale. And if you try to map out everything that possibly is playing a role, it can go easily 13 to 14 orders of magnitude in what you are observing, what you want to predict, and what is probably driving things at the micro scale. And this brings about a big challenge in how we set about answering meaningful questions regarding global climate models. That if you were to actually say that I'm trying to resolve these scales, you obviously can't resolve everything. So there is a certain kind of a bucket kind of a system where you're parameterizing these things with better done smaller scale models. And at every level, you have these parameterization, which brings in some kind of an uncertainty. And even before you start thinking about this parameterization, the questions are, what are the meaningful questions to answer when you're thinking of the small scale phenomena? And when I'll be talking about small scale, I'm typically thinking of problems that are involving cloud droplets or hydrometeors that are there in the cloud and how they influence dynamics that happen at the large scale.
So these people, people, they put a dabba between the blue and the green, right? Like cloud resolved models.
Yeah, so you can have, so I think I had, so you do have between LES and climate models, you can have models which try to, so I'll show some simulations which people have done where clouds are resolved. And this is, I mean, again, when you want to ask this question, I mean, the first part is, do we have a proper sense of what we think of as a cloud? And I was one of the fortunate ones who have heard Aaron talk about this quite a lot. And he was very eloquent in terms of actually explaining what is cloud dating back from literature, history, and he gave those perspectives. But I'm asking the question, what is a cloud, as a question to answer in science? And that itself, I have seen an evolution in how I've been thinking about this problem. That what do you mean when you want to say you want to study a problem in clouds? So Aaron's work primarily stems in understanding cloud as a fluid, cloud as a plume. And there is a huge volume of work where you are trying to understand this as a problem in atmospheric thermodynamics and fluid mechanics. Beautiful set of experiments, direct numerical simulations. Actually, one of the first instances I saw that this is a line of scientific inquiry was in the old EMU building. There used to be these overhead transparencies of Basu and Narasimha's work on plumes and jets, direct numerical simulations, which showed that you are basically, you can pose these as fluid mechanics questions and get something interesting out of it. Then gradually, with introduction to problems in low Reynolds number and particulates, I started thinking of clouds actually essentially is as a accumulation or as a cluster of particles. And this is what, when you look at the glossary of American Meteorological Society, this is exactly what they would say as cloud. I mean, it's a collection of water drops and ice crystals, which is suspended up in the air. But then the part where clouds play a big role is in their interaction with radiation, because that is the part where they are playing a crucial role in terms of the reflection that they're, whether it's the reflection at the cloud top or the reflection from the bottom from Earth itself. So there is a problem of scattering. So what you observe here, I'll come back to this picture a little later, is what are known as sundogs. So if you have a scattering phenomena that you typically see as a halo occurs when you would see a scattering happening due to randomly oriented ice crystals. Whereas what you see as a sundog here, so there are these bright spots at around 22 degree, from the horizon. And these happen primarily because most of the ice crystals are in a, by and large, a horizontal orientation. And this is something which makes you think that you can approach this problem in different angles. There are different lines of scientific inquiry, whether you think of them as problems in just a continuous fluid mass which is undergoing entrainment. There is a lot of exchange of water vapor and momentum. You can think of them as individual particles, or you can think of this as a problem in scattering.
So when you see that photo,
which one?
Next slide.
Oh, this one?
That light thing.
Yeah. I'll just go back. So this is something which is observed near the Arctic, but you do see, this kind of an asymmetric scattering phenomena. It does occur. So it primarily will happen where you have these icy clouds predominated in your atmosphere. And then if the orientation of these crystals are by and large horizontal, then it will give you this kind of an asymmetric pattern instead of a halo.
Know that 22 means horizontal?
20. Well, you can actually start by asking the question that if all these crystals were oriented randomly, then you'll see a symmetric halo. So the asymmetric halo comes because there is a bias in the orientation. And to get that precise angle, then you need to do a scattering calculation of that. If there is a crystal which is primarily pointing down, then if you have an incoming radiation, what kind of a pattern would you get? So that's a scattering calculation that you would need to do for that.
And why are they all on one radius?
You're saying why do they occur as if they're on a plane?
Yeah, as if they're on a circle.
So there is so you would see a complete bright circle if it was all symmetric.
So why would you see a circle? Like, why not just, why is that, what's special about that radius?
The radius at which it is being formed. What is specific to that particular radius at which it is forming?
What did you say it's called?
Sundog. Sundog.
Dog. Oh.
Yeah. So the asymmetry is in this brightness pattern. So you are seeing this bright. So if you were to see a circle which is illuminated perfectly, or you're seeing like a halo, that is what you would get if you have these crystals all randomly oriented in the cloud. So when there is a scattering happening, there is no bias in terms of what kind of a halo band would you actually see. But you get that asymmetry because there is a certain preference in terms of how the crystals are oriented. It's not like they are oriented in all random orientation. So this is regarding the cloud resolving simulation. So when you do these simulations, you can start sampling various kinds of length scales. You can start from the climate model simulation. You can do cloud resolved LES simulations. And I'm just trying to show the sizes that you actually start looking at. And then you can further do particles in turbulence simulations. And then you can say that, okay, fine. This is not individual point particles. They are particles which are of finite size. And you are trying to actually understand how these finite size particles navigate each other, because they can't really go through them individually. So there is an interaction between these particles. So the emphasis again is the range of scales that you have. And this basically brings about a big challenge in how you are trying to infer or how you're going to do these calculations. So before I move on to, the precise interaction problem, the first point is that particulate matter in the atmosphere can occur either in the form of droplets in warm clouds, which I will focus on very quick soon. But it could also be in the form of ice crystals in icy clouds. So if you have cirrus clouds can have a whole range of shapes, the shapes primarily driven by the ambient temperature and supersaturation. And just for reference here, you see like two snapshots of ice crystals. The prominent features are that in case of columnar crystals, they are extremely slender. They are a pretty high aspect ratio. And you can also have these stubby ones which have these rims that are formed. So as the crystals are falling down, they scavenge droplets and which supercooled droplets, which are then collecting and forming these rims that are getting formed in these crystals. And this is a paper which I'm particularly highlighting because it was a set of observations which was done at an observatory which was above the cloud level. So it was in Wyoming. So they did some very nice set of measurements of fall speeds of these ice crystals and even orientation of these ice crystals, which you can say as close to as making measurements out there inside the clouds. So,
just go back to that.
Yeah.
And they actually measured as a function of temperature.
The top one is different. Top one is not from these experiments. The top one is, a collated data of what shapes would you see given the ambient temperature and supersaturation.
So that's just from like various
nucleation of these crystals as they grow. So based on whatever is
but they are from clouds.
They are from clouds, collected from clouds.
Okay, and where did that appear?
This is a book, Pinsky and Kane. So I'm not sure where they sourced it from, but this is, in a sense that if you were to ask the question that how they are growing, I guess some of these also would be from lab growth of crystals, that if you were to tweak and play with temperature and supersaturation, mimicking what is happening in clouds, you would see that what morphology actually takes over.
Actually, you can even see that at ground level, right? Like
you don't have to. For this is
minus 20 and all will occur in a.
Yeah, I'm saying that you don't need to do this observation specifically for crystals that has fallen from clouds.
Right.
Even if you collect it from clouds, you would not know what ambient temperature supersaturation was there, which when it was present.
Yeah, it's nice to understand like how a certain shape comes
right.
from a certain. Yeah. Very nice.
So this is like again experiments which have been there for a while, but I find them pretty fascinating because they were exactly motivated by these questions of that if you have crystals which are falling in the atmosphere, they come and bump into a supercooled water drop and they collect these water drops. So effectively, this is what the question is: the mechanism by which the crystals grow. Do they grow based on just condensation that is happening, freezing that is happening on an individual crystal, or is it through collision with supercooled drops by which they are growing? So this particular work, in order to study that, find both fall speeds and also try to understand, they were looking at the orientation in the lab of heavily or ladder asymmetrically loaded rods. So they had a sphere which was fused on the rod, and the sphere, the weight of the sphere with respect to the rod was one parameter, which is plotted on the vertical axis, and the distance of the sphere from the midpoint is the other parameter with respect to the length, and that is plotted.
Fuzzy black thing, and what is that thing is the rod, the center one?
The center one is the crystal. So I'm just showing the image here on the left, which is from an experiment, the observation that was made from crystals in the clouds. The one on the right is an earlier experiment. I'm just I'm putting the picture there to show that what kind of an orientation do you have. Okay. So they were not working with images of this kind, or crystals of this kind. They had their experiment was a rod with a ball stuck to one end. So you have one parameter, which is the weight of the ball to the rod, and the other is where the ball is glued with respect to the midpoint.
And with that ice wala photo, what are those black things?
That's like there is drops have come and frozen, and it has created that kind of a mushroomed end, bulbous end is actually formed there.
Oh.
What's on the axis? Yeah, so the y-axis is the weight of that sphere with respect to the rod. Yeah, so you have like a one-sided dumbbell. So you are basically saying that the rod of the dumbbell is, or rather the weight of the dumbbell is scaled by the rod that is glued to. The x-axis is where you have placed it. So the point is, if you take a very heavy sphere and put it at the middle of a rod, it is not going to create any torque about the midpoint. It's just from symmetry, you will not have any torque about midpoint. Yeah, so the ones which are the crosses where it will fall vertically. Because you can see that is a case where x by L is very large, which means you have actually placed it almost towards the end. Like you're basically placing it as far off as possible. So there is a strong torque.
Very heavy compared to
And it can also, you can do both. You can basically make it very heavy and compensate for small x, or you can make it light and compensate by placing it as far away from the midpoint as possible. So that's basically the top region of the graph, the top right region, where the gravitational torque is going to make the CG as low as possible and it is going to fall vertically. The size, I am not entirely sure, but I think these were in millimeters, more than millimeters, I'm sure, because these experiments, at least the experiments from this group, Javira and Mason, they used to have these experiments of dropping various kinds of rods and spheres and everything and measuring the fall speeds. It's below a centimeter maybe, but definitely not very small. Yeah.
This is like a gyrotactic torque that is observed for microorganisms. But you said just now that
Yeah.
bottom heavy organisms.
Yeah, so I mean, I'm just saying that this is, I mean, even before I think of any swimming or anything, I just have a bottom heavy object. It would want, when I've dropped it, it would eventually, if there is no fluid mechanics involved in the problem, it would want to lower its CG. So effectively, it will attain a vertical configuration. So there is no, I don't need any fluid mechanics for that. Now, if there is fluid mechanics, there is going to be a hydrodynamic component to the torque. And the hydrodynamic component of the torque, if you look at the bottom left corner, when x is very small with respect to L, which is, it means it could be near the midpoint, or the weight of the sphere is very small. In either of these cases, the hydrodynamic torque actually leads to it attaining a horizontal configuration. So I'll come to that why it should be horizontal, but this is the observation. And then in the intermediate case, you can have an oblique settling. Now, these things matter because whether it's vertical or horizontal or oblique, that also plays a role in terms of how it disperses or how it falls. Because if it's a spherical particle, there is no such preference regarding orientation because there is no orientation to define. But when I have an anisotropic particle, its orientation dictates in the direction in which it is actually going to, it can have a transverse motion. So this is why the oblique orientation becomes important, that if you have a scenario where there is a competition between hydrodynamics and gravity, you can have oblique orientation, which can then say that it is not going to have a straight line of motion, or rather, it will not have a vertical fall of motion. It can have an oblique motion. So this...
The oblique one is always steady in this case?
Yeah, so here this is in the Stokes flow regime, or very low Reynolds number regime actually. So in that very low Reynolds number regime, the trajectories are all nearly steady. I mean, the unsteadiness in the trajectory will start creeping in when you go to moderate to large Reynolds number, where there'll be like wake-induced effects. So here the wake is nice and steady.
This object has only two planes of symmetry.
It's, well, I mean, what they had, yes, you're right. It has one plane. I'm not sure if it has two planes.
It may not even have two planes.
Yeah, the thing is just a single plane. Yeah. By adding that sphere, you have made it.
Sphere is not a ring.
Exactly.
Yeah.
So the question is, why should it have a horizontal orientation? Like in a case like in the hydrodynamic dominated problem, why should something actually fall in the horizontal configuration? Because at large Reynolds number, we know that the drag would obviously be minimized if it is falling in the vertical configuration compared to the horizontal configuration. So
also, like, just because the drag is minimized or maximized, I've never understood why that should be a criterion. Like, why should it want to do that? It can have an intermediate drag, right?
So at low Reynolds number, you can argue that, I mean, you would have the dissipation would basically be the least at Stokesian. The Stokesian flow would be the least.
You want to be in the least dissipation. Like, that's why, I mean, what is driving you to that choice?
So compared to, so for the same configuration, compared to a finite Reynolds, I mean, a finite Reynolds number and a zero Reynolds number, the zero Reynolds number will have the the dissipation, which would give you what the drag is in that problem.
Correct. But I'm saying like with different orientations, I may get different drag.
Absolutely.
But why should I choose the one which is minimal?
No, you don't need to choose. I'm just saying,
Not, right?
no, you don't need to. I mean, so the point here is that you are having a configuration which is from just without considering it too much, it would give you a higher drag than what would it be if it was aligned in the vertical configuration. So now if you say that these were living in a Stokesian world, which is reasonably accurate, because if you recall the picture from here, there's a scale for you to check. The Reynolds is not very large. At these sizes, you don't really have very large Reynolds number, and it can be definitely much smaller than the sizes you are seeing here, in which case you are living in a scenario which is highly viscous. So if you have a highly viscous scenario, then if I consider an object which is axisymmetric, then there is no way it will experience a torque due to translation. So this just comes from the fact that we in the Stokes flow, I can reverse my forcing and I reverse my corresponding boundary condition. So I will arrive at a contradiction that if I were to switch the sign of gravity, my assumed sense of rotation would violate with what I'll get after the exercise. So that inconsistency tells me that the only solution would be a null, that there is no rotation. Now, the moment you have a small amount of Reynolds number, this picture breaks. And this picture primarily breaks, you can first think of that there is an aspect which gets introduced in the flow, which is a wake. There are going to be wakes which will be there, which you won't see in a Stokes flow problem. In the Stokes flow problem, there won't be, the vorticity is always going to monotonically decay away from the boundary. There won't be localized regions of vorticity in the Stokes flow problem. So wake formation occurs, and now you imagine that you're looking at wake formation for an object that is anisotropic and which is in a sense inclined to its direction of motion. So the wakes are differential. You don't have the same kind of wakes at the top, I mean at the forward and the rear end, and the competition of the wake can make them rotate. There are two wakes, one is getting shielded by the other. So as it falls, if you imagine this is my anisotropic object, there is a wake attached here and there is a wake attached here. The wake that is here is getting shielded by the wake here. And then this surface vorticity that is there will create a torque, which will eventually take it to a configuration where the two wakes are going to neutralize. So that's an argument to say that any non-horizontal configuration would give you a torque. And that is going to lead to you arriving at a horizontal state. And you can argue this through detailed asymptotic calculation, which is what was done in a paper by Kayat and Cox. But you can also argue this based on symmetry, what it should be. You are saying that this is a problem where there are only two vectors. I have the settling velocity and I have the orientation vector. Now I need to construct a torque out of it. And this I am doing at low Reynolds number, which means I am looking at quadratic dependence on velocity. So the only way I get a pseudo vector is basically having this combination vectorial. This is the only possibility. So the asymptotics is eventually going to give you that prefactor. Whatever is multiplying u dot p into u cross p, that is the quantity which you get from the detailed calculation. So whether you have a fiber, whether you have a spheroid, whether you have a cone, all of those problems will give you that coefficient. But every object which is axisymmetric will eventually have a torque that will have that functional form. And from that form, you see the torque disappears in two configurations. One, when u is parallel to p, which means it is having a vertical fall in longitudinal orientation, or a broadside orientation where u is perpendicular to the orientation. Now, the vertical configuration is an unstable configuration. You give it a small amount of perturbation, like the inverted pendulum, it will go to the horizontal one. So this is the other way of arguing that why you should have a torque and what that torque should depend on. So,
can you send me the reference with step?
Sure, I'll do that. So this entire bit actually then tells us that there is going to be a dominance of anything that is falling to attain a broadside orientation. And this is something which you will always see in experiments, that even though we always start by saying that Stokes flow gives you indeterminacy, and you try to do this in experiments, it's a matter of waiting long enough, because every real problem will have some Reynolds number. So it will scale with the Reynolds number in a sense that how long you need to wait. So there are experiments which you will see in those sets of beautiful videos by Taylor of dropping fibers in a horizontal and a vertical configuration. And in the scale of that video, you obviously see them, the vertical one falling perfectly vertical because it's a very viscous flow with very small Reynolds number. But if you were to run this through for extremely large period of time, it will eventually rotate and come to a horizontal configuration. So in most scenarios where the Reynolds is not so minute, even if it's a Reynolds of 0.1 or 0.01, you are going to observe the horizontal configuration quite quickly.
And ice must be much bigger, no?
Yes, definitely, and it is in air.
Yeah.
So I mean, you would definitely have the Reynolds number not become. I mean, it would be small, but it is
The order one varies.
for the larger ones. Yes,
Yeah.
definitely for the larger ones. So based on the length, it would definitely become order one for ice crystals. Based on the diameter, it can still be quite small. So the inertial torque is what is responsible for this broadside settling. So that's the argument for why you see broadside settling. So we went back with this motivation of what was done in Javira and Mason and looked at experiments which were designed to see if we can do competition between inertial torque and gravitational torque. So the way this was designed was 3D printing rods, which in one case, it's not quite the shape that I have it here. So in one case, it was like two cylinders of different diameter fused together. So you have a bigger diameter, a fatter cylinder, which is at the bottom of a thinner cylinder. Or the other way you can do is introduce mass asymmetry. So when you print the rod, you introduce an air bubble. So it creates a pocket inside one part of the rod. So one part is like a homogeneous rod and the other part is like an annular part. So you are shifting the center of mass of the object. So you can play around with these ways to create mass asymmetry, either through geometry or through density. So the point is again here, as you play with an asymmetry parameter, if the asymmetry is very high, it would want to be in a vertical configuration. And if asymmetry is low, then it would want to be in a horizontal configuration. And so finally, you're going to have a shift going from the horizontal to a vertical configuration through this oblique side. And it actually turns out to be a pitchfork bifurcation when it goes, if you play around with the asymmetry. And this is what was showed up in the experiments. And you can use the theory I described earlier to capture this, that you just do a balance of the two torque and you will see that this is what the competition reveals. Now, this is the story or the background of settling, when you're just looking at settling of an isotropic particle. But then they are not actually in a quiescent medium. I mean, clouds are strongly turbulent fluids, and in those flows, so you observe from that experiment that I mentioned of that Zikmunda and Wali, and this is the setup in Wyoming. So it's at 11,000 feet, significantly high altitude cloud lab. And the beauty of those experiments is not only did they actually collect those crystals and measure their fall speeds, they also got this observation of the orientation distribution. That if you were to find out that how many of these crystals are horizontal and how many of these are vertical or oblique, they were able to actually get this kind of a data. So the ones which are at deviation of 0 are the horizontal ones. And you see most of them are horizontal, but then there is a tail. And these questions are interesting in terms of actually understanding the orientation distribution of an isotropic particle that is falling in turbulence. But it also becomes interesting with the primary motivation I said of understanding a scattering problem. That if you know what is the distribution of how these crystals are present, you can then start answering questions that how would a radiation interaction occur given that the distribution is of a certain kind.
So how will you distinguish ice and snow?
How will you distinguish? I mean, in the clouds, it would always just be ice
When
crystal.
we see it, we think the more transparent one is ice, but how do we know, like, these guys measure? They're sitting in a snowy place, so how do we
okay. I mean, you're asking like when they're collecting it, and is it, so I presume it's proper.
Does it matter? Like, radiation, it's going to matter. That's why I'm asking.
Yeah, so I presume when they're collecting it, I mean, it's being collected at level where there are clouds which are already present. So you are either above the cloud level or you are pretty much at a level where you have clouds around. So when you are sampling and making these collections, they are probably not in that precipitating snow stage yet. That's, I mean, I've not check carefully to see that whether they are doing this when you have a snowfall or they are doing it by sampling it in the cloud itself.
But in the cloud itself, snow can form, right?
Yeah, but I mean, so it's like the question of saying what's a cloud droplet and a rain. So I would just say that it is when they are precipitating. The snow also would have ice crystals,
Right.
but it would be something that is large enough that it is precipitating down, like it overcomes gravity and falls down. So if I were to just collect snow, I would see the snowflakes have these nice crystalline shapes. So in the clouds, they would be probably smaller in size because they have not yet managed to overcome the turbulent randomizations to and fall due to gravity. So the left one is the set of observations from Zikmunda and Wali. And on the right are experiments done in the lab of dropping an isotropic particle in a water tunnel. So this is not air, it's in water. There are some differences that water brings in compared to air, but yeah, and also the fact is that there are more fluctuations that you will see in air. There's a set of recent experiments that have come out on doing very similar experiments, but dropping it in a turbulent airflow. And what they observe is that because the inertia becomes quite significant, you can have a lot of fluctuations in the motion than the damped behavior that you would see in water tunnel. So in the turbulent flow, you have falling anisotropic particles, and the idea was to again measure the orientation distribution. And you see that the orientation distribution starts to get flatter as the turbulence intensity is increasing. So it's when the PZ is cosine of the angle with the vertical. So as you have so PZ of 1 basically, so that's when it's in the the angle with the horizontal plane. So PZ of 1 basically gives you a horizontal configuration, and then you see there is a tail of objects or crystals that are aligned obliquely, and the distribution effectively gets modulated by turbulence. So again, the same question that is it possible to explain how turbulence alters this orientation? So if you say that they are by and large going to be horizontal and you try to calculate the fluctuation, can you actually get a measure of this fluctuation based on the turbulence intensity? And can you try to, in some way, get the distribution that you would observe in some ways from the experiments? Can it be replicated by theory? And that's what we set about doing. So I'm just showing here, yeah. One snapshot of turbulence. No, you're averaging over many realizations. Yeah. So what we went about studying was the orientation. These are like some pictures of 3D printed anisotropic particles that you can make in the lab. We were looking at rods and things which were like more Y-shaped. So Y-shapes are, a reason for studying Y-shape is also convenience of experiment, because Y-shape is a planar object which mimics a disk and an oblate spheroid. So it's kind of mimicking an oblate spheroid because you can make it into a Y. So it has the symmetry necessary for the fluid mechanics of a disk. And it's also easy to track, because in a disk, you would need to make markers and then track its orientation. Whereas for the Y, you just mark those rods and you track those rods. So it's convenient from a visualization perspective, but you can drop all kinds of shapes and study their orientation dynamics. And these are quite nice experiments that can be done. So what we set out doing was ask the question that if you drop this kind of a triad, so it's that Y shape that I was referring to, it would want to remain horizontal if there was no turbulence. And as you have some role of turbulence, it's going to fluctuate. So this quantity which is plotted on the y-axis is its deviation. So 1 minus cosine square theta tells us that how much it is deviated from the horizontal plane. So that object should go to 0 if there was no turbulence. And as turbulence becomes strong, it should become isotropic, because turbulence would basically give it a complete random orientation. So this is what you observe. So the idea here was to see that how it depends on the settling speed. So there would be a certain scaling which was known previously in the literature of, so the x-axis is a measure of the settling speed. It's a proxy for the settling speed. So you see that there is a trend that it observes with the settling speed, and we were subsequently able to use this and construct the distribution function. That how do you get the orientation distribution function for these ice crystals in a turbulent flow undergoing a settling behavior. So this was the story for what we have been doing for rods. Now,
Settling
yeah.
speed means turbulence is unimportant or what?
No, this is not fast. Oh, SF. I mean, the x-axis being large. X-axis being large basically means that the turbulent velocity is smaller than the settling velocity. So it is falling quite rapidly through a sequence of eddies. Yes.
In the limit of Reynolds tending to infinity.
Reynolds tending to infinity. Yeah.
I mean, though you can do simulations, what is the expected?
So you are saying that the Reynolds based on the particle size tending to infinity.
No, the large scale.
Oh, okay. So the large scale expected is that it should be so. It's not just the Reynolds number based on, so let's say the Taylor Reynolds number for these problems. The Taylor Reynolds number for the problem when I'm writing the simulations, they are a few thousands. So you can push that. You will get curves which will almost try to converge. But the point is, there is one which is the large scale Reynolds number. The other is the parameter which is the ratio of the settling speed to the turbulent characteristic velocity or the Kolmogorov velocity. So to say that as the fiber falls, how quickly does it fall through an eddy before it actually makes one loop, one rotation. So that's also an important parameter, because you can have a very large scale Reynolds number and it would be inconsequential if the object still continues to sample several eddies before they are actually making one complete revolution. So that's the parameter SF. But yeah, I mean, we have done, so just for a detail, I mean, the calculations that we did here, the theory you can do based on properties of homogeneous isotropic turbulence. For simulation, we used a velocity gradient model, which was primarily targeted to make sure that there is, it's capturing the log normal behavior of the pseudo dissipation. So we use that because the fibers are responding to, they're small enough that they respond to the velocity gradient. So then we could play with what is the large scale Reynolds number. I think few thousands, I think 2,500 is probably the largest we explored in these cases. So that was the story in brief about anisotropic particle. I tried to condense regarding what we have been doing for rods and their behavior due to asymmetry, their behavior due to interaction due to turbulence and settling behavior. But the broader question is, can we do these hydrometeor physics better? And the part which is something that has been occupied us for a while is trying to understand the interaction problem. And interaction problem, obviously, we are starting just with cloud droplets. We are not even thinking of anything asymmetric here. And that itself has a significant amount of challenges. So if you're just asking the question, what is it that you want to answer here? You have the activation of the cloud condensation nuclei that gets advected due to the updraft. And then condensation basically kicks in. It is in a supersaturated environment. These nuclei start to grow. Now, if they were very large, which is 50 microns, so if you do an estimate that what is the settling speed of a 50 micron drop, that typically would be a value that will exceed the Kolmogorov velocity. So that's why the number around 40 or 50 is what we say, that that's the size beyond which it can fall faster than the velocity of a typical eddy. So beyond that, gravity is dominant. So it's going to fall. And as it falls, it could collide with other smaller drops and grow in size and eventually form a drizzle, which becomes like a raindrop. So raindrops would be, depends on the wind condition, would be millimeters. The largest would be like 4 to 5 millimeters, but half a millimeter to few millimeters is the range that you're thinking of. So the picture is quite well known to some extent, I would say, in the very small size and in the very large size. There are aspects that need a lot of study in those aspects too, but the challenge is bridging the gap in between. That what leads it to actually go from this size to the larger size, from a 10 micron size to a 50 micron size, and what would explain that physics. So this is something which is known as the bottleneck in trying to resolve that if you go from a condensation to a gravity dominated picture, how do you resolve this bottleneck and what possibly plays a role in resolving this bottleneck? Now, if you just take a condensation picture, what's the issue with doing that? Because condensational growth will get slower with increasing size. I have a larger drop. I basically have more surface area. So I effectively have a much slower growth compared to the smaller drop. So the condensation growth becomes weaker and weaker with increasing size. It also has one more issue, is that if you don't account for any fluctuation in supersaturation, then it will give you a very pointy distribution. You start off with, let's say, a monodisperse size. It will remain largely monokinetic all the way through. But that's not what you have from observations. The observations give you a fairly widespread of distribution. Gravity is what will give you a growth that increases with size. The larger the size, the faster you will have the rate of growth due to differential sedimentation between larger and smaller drop. So it's resolving this challenge. And this is the part regarding what you get from experiments. So this is a set of experiments done in the CAPEX expedition done by IITM Pune, where they had aircrafts flying through clouds and making measurements of droplet size distributions. The legend that you have, the first set of digits, they are usually going to give, so I think, yeah, so they give you the time in UTC, and the last 4 digits give you the altitude in meters. So it gives you the height at which they are sampling these distributions. And if you are just looking at the pictures, if you are moving in time, the distribution is going towards larger sizes and getting broader. So this, yeah. Understand which peak? The red. Yeah, so a drop so I have a population of same size drops, and they are growing due to condensation. So if I say that the supersaturation is constant, there are no spatial fluctuations in supersaturation, then in a constant supersaturation, everybody will grow to the same size in the same instant in time. Everybody is accessing an infinite reservoir of supersaturation. So in a same period of time, at 5 micron, if it grows to 10, my neighbor also will grow from 5 to 10. Their neighbor there also will grow from 5 to 10. So which means that if it is monodisperse at t equals 0, it will be monodisperse forever. Yes. Then there will be a broadening. Some broadening will be there.
So that would be explained by.
No. So you can say that it's a condensation-driven theory, but it's a condensation-driven theory which is accounting for fluctuations in supersaturation. Let's say it's because the supersaturation is a scalar advected by the turbulent flow. So as the turbulent flow sweeps around the water vapor around, you are basically going to find, differences in supersaturation, and that can lead to, a broadening of the peak. That is the, so drdt is the relative, r is the separation, or you can basically say, the rate at which it is growing. So it says that if your radius is r, then based on your differential velocity, you are going to grow at the rate of r to the power 4. Because the relative velocity between two spheres would scale quadratically with the size. Right, I am saying that my settling velocity is proportional to size squared, because it's the mass divided by the Stokes resistance. So mass scales cubic with size, resistance scales linearly with size. So I get a quadratic dependence on size. Now I have to find out the flux, the particle flux through a collision surface. The collision surface would scale with r square. So the r square and r square gives me r to the power 4. So I have a smaller sphere, I have a larger sphere that is coming. Their relative velocity scales with the size square and or the average size square, and the size of the collision sphere also scales with the r square. So that gives you a net flux, which would be the 4th power of it. Yeah.
turbulence decides to fluctuate so understand how, but I don't understand this.
So I'm saying that in the idealized picture that I have here, I'm saying that every drop is sampling the same supersaturation spatially with no bias whatsoever. But if you say that the supersaturation is not in a still air, I mean, it's in a constantly being churned around by the background turbulent flow. So then you are going to have differential sampling of the supersaturation mediated by the turbulence. So the turbulence here is mediating through fluctuations in supersaturation. I'm not discussing yet about what the turbulence does to the particles themselves. I'm just saying that if the turbulence were to just move around a scalar field, then I mean, both of us will not necessarily see the same kind of supersaturation. We will see some fluctuation amongst both of us, and that would show up because then eventually you would have start seeing disparities in growth that would come in. So if I were to grow a little bit to a larger size than what you would have grown, then my rate again, so because the rate is again determined by the size. So that can bring about a broadening. But that broadening will not necessarily capture the kind of broadening that you will see for the sizes on before the onset of precipitation. So this would require, what is it that you need to do to actually attempt at getting some picture of droplets as distribution? So you would have to say that these drops are colliding, and these drops, when they are colliding, as they collide, two drops of different size, if they collide, they are creating a drop of a different size, but they are also depleting a drop of the size that they were originally. So this is what is like a Boltzmann kind of a picture of collision, that you are losing something, you are gaining in some other size phase space. So you solve this evolution equation where there is nucleation, there is condensation, and then there is a collision. And the part that you need is the collision kernel, which tells you that given two drops of sizes and the ambient atmospheric condition, which is now your turbulent dissipation and the large scale Reynolds number, with these four parameters are the primary four parameters which will fix the value of K. You don't need anything else because it's water drops in air. Everything else is fixed. So the only four parameters are the two drop sizes, Re lambda and epsilon, the dissipation. So this, if you have in your, from a detailed calculation, can then be fed in order to create an evolution of drop size. That I start off with something which is very peaky, a monokinetic kind of a distribution. Let's say condensation has brought me here. And then I will gradually start evolving to a broader and a distribution whose mean also starts to shift. Because condensation will not allow for just the condensation, regular condensation will not allow for a migration of the mean. Even if it has a slight broadening, the mean will still be what is, it's not really going to shift to larger sizes.
Can you explain the second integral?
The one which is the last one. So the last one says that if I have two drops which are colliding, then I lose out from that particular size. So, I mean, I have a 5 micron and a 10 micron comes and collides. So I'm obviously going to gain in a larger size once they collide, but I'm going to also lose out on the size that is, which was originally a 5 micron drop or a 10 micron drop.
0 to 8 is all the drops smaller than me.
Right.
And so like they all become means. That what is this?
So anything that is between 0 to 8.
So that's a gain term and this is a loss.
Loss term. So you have a gain and you have a loss in the thing because of collision. A key assumption here is everything is assumed to coalesce because collision doesn't imply coalescence. But again, if you are looking at drops which are below 100 microns, the coalescence efficiency is typically very high. I mean, it's around 90% or higher. So we are looking at that for the sizes that we are interested in. It's a reasonably good assumption to say that anything that collides would always coalesce. This will definitely fail if you go to raindrops. That will not be the case. And just one more assumption I want to clarify. It's also not taking into account any aspects of fragmentation, that breakup of, and which will again happen when the drops are quite large. Yeah, there were a few questions. Yeah.
What is A double prime?
Which one?
A double prime.
Yeah, so that's basically like a a size that you are losing out from. Is the distribution of drops of a given size. Yeah, so if I have like 2 drops as they come, they can bounce off. So it depends on because you're finally having a competition between your surface tensions. When you bring it closer, it will depend on the inertia of those particles as they're getting closer. So now as they come closer and they squeeze out the fluid in between, will they drain out all the fluid and they will fuse and form a nice drop? This will only happen if the drops are very small. If the drops are quite large, then you can have all kinds of things happening. They can come, they can collide they can fragment out. You can have like one bigger one getting fragmented by hit with a more impulsive smaller one. So these things, assuming that coalescence will always occur is not true once the drop becomes quite large. Yes, yeah, that's a good point. So I'll come to it. So everything here assumes, so okay, the formulation here is basically just saying that what is the rate of collision given the size. There is no evolution that you are studying in any other variable, or size is the only variable that you are looking at. So you are saying I have 2 drops. They come and collide of given size and they have formed a larger drop due to the process of collision. Now the question is, the collision that you are trying to calculate, does it actually need to account for whether it is rigid or it's a drop? And if it is a drop, do you also account for the fact that are they deforming or are they not deforming? Exactly. That is all going to be factored in the kernel. All of it would be there in the kernel. This is just saying that given 2 objects of given size, you are writing a rate equation. You're saying 2 objects of given size, they come and collide, and I'm assuming it's 100% coalescence the moment they collide. Yeah.
How do we know that only convention?
So if there are no fluctuations, then I just basically have I will have a change in the location of the mean, but it will be very slow. I have initially 10, all the population just moves and becomes 12, then they'll become 15. So gradually there's a shift, but the shift will be slower and slower. It will get increasingly sluggish as the size goes up. The width, if you say it's perfect constant supersaturation, it's a delta function, it remains a delta function. You need to account for some fluctuations. Either you are doing fluctuations which are due to Brownian motion, which kind of becomes negligible for 10 microns and all, or you say it's fluctuations in the turbulence. Fluctuations in supersaturation induced by turbulence. It would just be like a front which is propagating but getting slowed down. Because you can think of it that way, right? If you just look at this equation, forget all the kernel, then it's a 1D wave equation where the wave velocity is 1 by A. A dot is actually 1 by A. So you're solving a 1D wave equation which has a wave speed that gets smaller and smaller as you propagate outwards. Okay. So this is a question which is not recent. This is a question which has been around for quite some time. And the earliest evidence of this question comes from one of Langmuir's paper around 75 years back, where he precisely pointed this out in this explicit scenario of cumulus clouds, that you do have rain formation in less than 30 minutes, and this mechanism cannot be explained based on a condensation-driven theory. So just the identification and the statement of the problem was already there in the literature quite long time back. And it continues to be something that is of interest in terms of resolving this. And I'll come towards the end that once we resolve, what do we take forward and go from here? So if you have particles in a turbulent flow, you are going to have particles preferentially sampling the flow based on regions of vorticity and strain. So you will have these kind of cluster formations. And the cluster formation basically now asks the question that if I were to zoom into one of these regions where they have clustered, how are the particles actually going to collide? So this is actually asking the question that now I'm not talking about them as point particle, but as finite size objects. So what will bring them together? because they perceive the presence of the other particle. So you would think, what would drive the collision? What is it that actually plays a role in terms of dictating what the collision is? So there can be a whole array of physics that drives collision. You can have the fact that these are in a turbulent flow. So the turbulence somehow manages to bring them together. But then you ask the question, okay, if they've been brought close together, what would make them collide? There can be colloidal forces like van der Waals playing a role. There can be the fact that these are drops, not rigid particles. That can be important. And you can also have charge effects also playing roles. So there's a whole zoo of things that can actually lead to collision. And as I said, eventually the objective is to create like a table of collision rate given sizes of given two sizes and values of dissipation rate characteristic of clouds and the large scale Reynolds number, a lookup table, which someone can just use and basically run and do these kind of droplets as distribution. So the idea of doing this calculation without accounting for any interaction started out with Smoluchowski's work, where it was in the motivation was in coagulation or in colloids, that you have two particles and they are actually trying to collide with each other, and they move as if the other particle was never present until they hit. So it is completely oblivious of the other particle till the instant it is making contact. So which is why they're called as ghost collisions in some way, because they are not really collisions that are happening, because they would never move along those trajectories. So if you have a gravity problem, the bigger drop is going to just move in a straight line in the reference frame of the smaller drop. And there is no deviation, there is no deflection due to the small drop. And it goes and bumps into the smaller drop and you get a collision. So it's...
I also thought they call ghosts because they walk through each other.
Yeah, so they are basically like passing through it. They are just passing through it as if the other one was not present. So you can calculate the collision in a purely geometric sense. All you need is the geometry of the flow and you can calculate. So here in the gravity problem, which is what Smoluchowski did, you just need the cross section of the cylinder. Yeah.
But if the two drops collide, when they coalesce into a single drop.
Yes. So you are just asking the question that what is the rate of collision?
But they're not walking through each other.
Yeah. So the point is that they're moving as if they can move through it. Post the collision, I mean, you are not answering anything about post collision. You're only answering the question till the event of collision. So you say that they go and they're approaching as if the other one was not present. It's like just a spherical region in space and I'm moving through that region. The moment I hit the boundary of that sphere, I call it a collision event. So that's basically the idea of Smoluchowski's, and it can be used to get collision rate in various kinds of problems. So I've listed out what is there for gravity and what can happen for simple shear, that you just find that intercept area purely from a geometric point of view. But this is not exactly what happens when you are thinking of particles in a flow, because particles are finite sized. So as they get closer, you are going to see all kinds of deviations from the trajectory as they get closer, because the flow field has to satisfy the no slip, no penetration boundary condition on each of the spheres. So you have to solve for a problem that is consistent with that. And this is something which has been developed quite rigorously in low Reynolds number theory, people looking at suspensions. So in a completely different scenario for looking at suspensions, this is where the topology of these trajectories become important, because they play as a feeder in either finding coagulation or answering questions like rheology, that you want to find stresses, etc. So this is like the story of how these interaction calculations can be done.
Go back to the previous slide.
Yes.
I mean, okay, I can understand them moving around the other particular. Why did they go back to the
Okay, so the thing is, in this particular flow, so it depends on the flow. In this particular flow, there can be two kinds of trajectories. So you can have a trajectory where it comes from infinity and makes a deviation and just goes around. No, but you can also have where it gets caught in an orbit and it makes an orbital motion. So you have this one, the one on the left corner is that orbit. But this is very specific to the kind of flow that you have. This is a flow where you are trying to shear it. Like imagine you do what you call a simple shear flow. I'm moving the top surface related to the bottom surface. So I create a flow that is a simple shear flow. And in that flow, you can see this kind of flow topologies. You do a different kind of flow. For instance, you see the one on the left side, on the right side. Here, you are trying to compress it from the top and pull it out in the plane, in the horizontal plane. So here you won't see any trajectories which are orbits. So what kind of trajectories you have, that crucially depends on the kind of flow that you are looking at. So this is, I mean, something which is quite well studied in suspensions of looking at particle dynamics at low Reynolds number. And there are ways of looking at it. But this brings about a problem in what is our goal. Our goal is to find the rate of collision. The problem is the following, that if these two particles were approaching each other, they create a small gap. And the gap is getting smaller and smaller. So now the question is, as the gap gets smaller, if I'm trying to drive it with a constant force, let's say sedimentation is the problem I'm interested in, I'm trying to drive it with a constant force, the velocity of approach will go linearly with separation. So either you think in terms of velocity or you think in terms of the force. That if I make them move with a constant velocity, then the force, which is the lubrication force, scales inversely with the separation. Now this means you are never going to contact. You're never going to reach a contact between two surfaces. Now, this is never a question that anyone needs to think about when you do colloids. Because in colloids, you have van der Waals. You have van der Waals which is at play. So the moment roughness can be there at play. So whenever they get very close to each other, you will have these non-hydrodynamic forces which are going to account for the fact that it will overcome the lubrication effects, and you will get some kind of a coagulation that was going to happen. So is it?
Lubrication effects
are
not, I mean, even if we pretend that it is continuum till they attach and no other forces are there, even then lubrication theory fails when the distance is very small.
Very small compared to?
Compared to the radius.
Yeah, so the lubrication theory will just tell you that as you, because that
yeah, no, what I'm saying is in lubrication theory, it's something like a shallow water theory, where you're saying gradients in this direction are very small
compared to the vertical one.
In that direction. That's no longer true when it comes very, very close.
I mean,
any pointy thing, like two things are trying to meet.
Right.
It's no longer true that. So you cannot apply lubrication till the end, although people apply.
No, it will depend on the curvature that you have. Exactly. So if you have a perfect sphere, then the radius of curvature or the curvature is a constant. So you will always have a region near the contact where still the gradients in the horizontal direction are smaller than the vertical. But if you had like a slightly pointy particle, then I agree. I mean,
the problem is that the extent over which that thing is there will be very small, and the flow that's oozing out.
Yeah, so you will
no longer be parallel, so you can't say it's parallel.
You are right, but there will still be, I mean, if I have a small gap, I will still have a horizontal extent which scales with that small gap where I will apply lubrication. But the outer region, I mean, will contribute. But the contribution.
We found that it won't follow this linear thing when you come with it.
But purely from hydrodynamics or something else?
We've got we've improved those equations. I'll show you later.
Okay, because I mean there are deviations which will come in if you say they are soft, or if there is inertia, if there is particle inertia, because then also particle inertia will change things. Correct. Yeah. Because then what happens is you are
no longer parallel those streamlines.
Okay, because particle inertia can actually make lubrication become important at such small length scales that it is no longer a lubrication problem. You can actually bypass the lubrication in some sense. Like if I drop a ball and the ball is hitting the surface, the question is, does it really experience a lubrication the way I'm describing here? It doesn't. I mean, I'm saying here that there is an infinite time approach of the two surfaces. And we all know you don't need any asymptotics to know that a ball will make a finite time contact because it has a finite inertia. So that inertia will be so large that by the time you are able to overcome, I mean, there is acceleration and there is drag. So by the time the drag is able to overcome the acceleration term, you would have gone to extremely small length scales where van der Waals and other things will become important. So you don't really have that kind of a phase.
But I'll show you this thing based on geometry.
Sure.
On the lubrication.
So the question is, what drives the collision? You can do a balance of different forces that are present, and you can argue that is it van der Waals which will always drive collision, or because these are drops, the drops can deform. So there can be deformation of the drops which can make them collide. Then the lubrication pressure could be comparable to vapor pressure, which would mean that the flows are becoming compressible. Or you can also have the scenario where the fact that there is a flow that is occurring inside the drop. It's not a rigid particle. There is some kind of a circulation inside. Would that also be responsible for weakening the lubrication force? And all of these can lead to collision. It's known that these all physics will lead to collision, but it's on this scale, what we see is that if drops are not particularly very large, van der Waals seems to be the winner. And this is exactly what is the story when you do colloids, because you're doing particles in aqueous medium. But when you do aerosols, you have the other aspect to account for, that there is a mean free path of air molecules, which would be around 100 nanometers. So by the time van der Waals becomes important, you can have a size range where the non-continuum effects are actually becoming quite important compared to all other physics. So you can have two surfaces approaching each other, and in that lubrication region, you should not be doing the regular Navier-Stokes equation. You should be actually solving for an equation that accounts for the non-continuum physics. And this is the part which also, based on the fact that we are doing aerosol problems, you have lying in that 10 to 40 micron range. So in that sweet spot where collisions are actually important, the collisional interactions are actually driven by non-continuum effects rather than any other physics that there might be.
So, like, suppose you're looking at a 1 micron.
Yeah.
Can you explain, like, h is the distance between?
It's the distance between the two spheres.
So if the distance is very, very small.
Right.
So you're saying non-continuum effects are important everywhere below the line.
Yeah. So I'm saying that non-continuum.
Below the line.
Exactly. So other physics will definitely come in. It's just that before they come in, non-continuum effects will become important. So for very small particles, van der Waals is the key thing. If you have particles which are hundreds of nanometers or smaller, then you have van der Waals actually will drive their collisions.
And is this true for any material, like if it's solids?
It is true for any material as long as the material doesn't have any other kind of attractive potential between them.
Right.
I mean, if there is something else which modifies the van der Waals, so the van der Waals curve that I've drawn here, that is material dependent because I've done it for water drops in air medium.
Van der Waals is just because the hydrogen likes to, I mean, that Y in the B in the water drop.
The dipole has the interaction which gives you the van der Waals forces.
So basically, it attracts and it overcomes surface tension, is it?
It can be more important than everything else for very small sites.
Where is surface tension in all this?
Surface tension comes through deformability and interface mobility. So you can have the drops deforming because as they get closer, the lubrication pressure makes it move away from a spherical shape. And it can also come in because the fact that these are drops, which means there is a flow inside. So the boundary is not a no-slip boundary, but rather a stress boundary condition. So the stress boundary condition weakens the lubrication force. It's not as strong as a rigid boundary lubrication force.
So you're actually saying that if it is half a micron or tenth of a micron, non-continuum is important. Right, that's 100 nanometers.
Yeah, so from, I mean, this black line that it's,
Yeah,
I mean, this is roughly you are starting at, I mean, around 1 micron to around 40 is the range where it.
I'm talking about the y-axis.
Right, that is 100 nanometers.
100 nanometers, yeah.
It's the separation.
Yeah.
So it around 100 nanometers, it becomes important. So this is never something you think about in the aqueous problem because the mean free path is so small that it is irrelevant for the purpose of understanding adhesion or collision because van der Waals is always going to be more significant. The mean free path is in angstroms, water. I'm talking about in colloids literature. In colloids,
solids in water.
Then the mean free path of water molecules is insignificant compared to anything else you do.
Angstrom or something.
So you always do Navier-Stokes with van der Waals.
Right.
You never have to do anything else. It's not a question you even think about. But when you're doing a gas solid or you're doing these aerosol problems, then the picture flips purely in the lubrication problem. So this is the modification. So we say as the gap gets smaller, you solve a continuum fluid equation in the exterior, but in the gap you are solving a non-continuum equation. So by solving that, you are able to now get a lubrication force which gets weaker. And the weakening of the lubrication force is something that is not as strong as the 1 by separation that you get in the continuum theory. It's a weaker separation that depends on the Knudsen number. And the question is, does this kind of a divergence matter? Like you're getting a weaker divergence. Do you care? I mean, is it just a mathematical artifact or mathematical feature of having a weaker divergence? So if you go back to the argument that I have a relative velocity that depends for a given force if I'm trying to move two surfaces, if the lubrication force went as 1 by separation, I will never see a finite time contact. But if the lubrication force went weaker than 1 by separation, then I'm going to get a finite time contact. So for precisely calculating what is the rate of collision, the detail of modifying or looking at the lubrication effects is important. And then you can take this forward and now start looking at problems. You can basically say I have two spheres in a background flow with sedimentation being one of the physics, and also maybe there are interparticle forces that are there. So here R is the separation between the two spheres. So there are two spheres. The relative separation between the two spheres is R. Gamma ij is the background velocity. So if there was no interaction, then the two spheres will move according to the flow. So Ri dot would be gamma ij rj. That's all that it would be. But because of interaction, you have this additional part where A and B, they depend on the separation. And they're known as these mobility functions, which tells us that far away, A and B will vanish. But when you are in the close approach or near field, they become quite dominant. So they are going to make sure that you just can't come and bump through it. So that bump through or the ghost collisions are going to be completely avoided because of the fact that you are now accounting for interaction. And the non-continuum effects are now included in these mobility, precisely in the mobility A, which actually has the non-continuum feature. So this curve that I showed you, this curve is something which takes you from the non-continuum regime when the gap is very small to the continuum regime when the gap becomes very large. So you are uniformly creating this Mach asymptotic way of finding the total force between two spheres, and then you can use that to find that given a force, what would be the relative velocity.
A and B have the one level effect.
No, A and B is the mobility due to flow. They are the mobility functions due to a background flow where E is the rate of strain tensor, gamma ij is the velocity gradient. So they are actually telling that given a background straining flow, so if I have a rigid body rotation, I will never have hydrodynamic interaction. If I place two spheres in a solid body rotation, there is no interaction because it's purely a tangential motion that they're undergoing. Only when I have some kind of a straining will I see interaction. So that interaction is actually captured in the second part. So A and B are functions of size ratio of the two spheres and their separations. It's how easy is it for me to actually approach the other sphere as I move around in the flow. Yes.
Then how do they prevent ghost collision?
Because A and B are not zeros. If there was A and B were zeros, then it would be a ghost collision, which means that I can exactly move along the fluid streamline. And if the fluid streamline were to intersect through this imaginary spherical surface, I'm going to pass through it. But now as I move, there is A and B, which are the interaction terms, which are going to become significantly large. Well, not large, they're going to become important. Let it put this way. They're going to become important such that I'm going to slow down. Ri dot is going to basically the relative velocity is going to slow down as I approach the other sphere.
But A and B themselves are not functions of R. Right?
They are functions of the separation and the size ratio.
They are functions of R.
They are functions of R. So they go to zero in the far field, which means there are no interaction. And in the near field, they become quite dominant. Yes. Yeah. Charge-based things, yes, definitely. That's a... Okay, so that will depend on the net value of your charge and also the charge ratio that you have. So you have to ask the question that how much charge can it hold? So that gives you the net amount of charge content that is there. And then the charge ratio. So what we have observed is that the charge ratio plays a big role whether big, I mean, and they can be quite, can have quite dramatic effects actually. So it's captured through this kind of a formulation where you say that the relative velocity is driven by some central potential. It could be electrostatics, it could be van der Waals, anything else. Even Brownian motion also can be modeled here. You can say that there is a relative velocity which is driven by a gradient of a potential, a thermal potential. And you can have sedimentation also being incorporated. So you can have all of them together, in which case you are now saying that I have two spheres which are moving in a flow, settling due to gravity, due to some background or due to some central potential. And I can find out that how they are actually moving around. Now, once you know how they are moving around, you can ask the question that what is the rate at which they'll collide if they start off from infinity? If there is one sphere, I'm fixing my coordinate system at one sphere and I have the other one coming from infinity. What is the rate at which they will collide? Which then gives us the calculation of what is known as a collision rate. You are trying to find out the rate at which they are going to collide, given that the other sphere starts out from infinity. So this goes back to the original thing which we said about the kernel, that if you are calculating the collision kernel, this is what the collision kernel will actually be. You give the sizes, you give the properties of the flow, and if you have any other parameter like, let's say, charges also involved, you can include that and effectively you get that collision rate. So this is a typical calculation of the flow being a uniaxial compressional flow and settling being there. So as you move along the x-axis, you are basically getting a flow where settling is becoming more dominant than the background shear flow. And you have the y-axis is the collision rate with interaction, how dominant it is with respect to the ideal value. The ideal is the Gauss collision value. So you see that there is a significant dip in the value. So you will have a dip which will give you a, so Kij subscript, superscript 0 is what Smoluchowski's calculations are. So with respect to that, you can have the value actually dipping by a factor of 3 or 4 easily due to interactions. So interaction plays a very prominent role when you are doing the calculation, especially you are trying to get a precise answer for what the collision rates are. Now this is all in a laminar context. There was
Yes, you're always seeing that collision rates go down.
Yes, unless you are including charge. The only case where you have seen is that charge can play a big role if you are looking at collision, where they can make the collision efficiency significantly high.
Because like if you'd asked me on the street, I would have said Brownian motion will increase the collision rate.
Yeah, so the collisions are getting lowered with respect to the no interaction problem. So I'm always facing difficulty in colliding with someone because I have, I have to basically, I'm getting deflected.
That's because of the deflection. But
Correct.
suppose I just had Brownian motion.
Right.
I would say that the chances will go up, right? Like we're exploring motion.
Yeah, but I'm saying that interaction is going to inhibit it in some way. So just pure Brownian motion, yes, Brownian motion is going to give you, but if you're now trying to compare the efficiency of Brownian motion with and without interaction, then it will, So
only charge is the thing.
Charge actually...
Van der Waals makes them hate each other.
No, Van der Waals definitely is increasing. So the point is the Van der Waals becomes important when you are asking that, how do I get this collision efficiency? See, this collision will not happen with interaction unless you do non-continuum or Van der Waals. So you are resolving the near field interactions to get the collision rate. So if you do a Van der Waals calculation, the Van der Waals plus non-continuum will be slightly below the black curve. Just Van der Waals without non-continuum will be below the black curve. So you'll get that kind of a modification. But the trend will be the same. It will not give you a non-monotonic trend. Whereas charges can give you non-monotonic trend. So this is all the story for everything being laminar. The flow was laminar. Even though I motivated it with the clouds problem, there was no turbulence that was there in the picture. So, and clouds typically are a very peculiar kind of a turbulent flow. It has a very low dissipation rate, very large scale Reynolds number, and which effectively also you're getting a very large Kolmogorov length scales. So when we are thinking of the typical length and time scales for clouds, the droplets that we are interested in, they are living in a sub-Kolmogorov world. They're living in an eddy where they see an unsteady viscous flow. Because the size of the drops, if you say they are around 40 microns or smaller than that. The eddy is typically a millimeter in size. So they are not seeing anything that has strong effects of inertia in their neighborhood. But the flow is stochastic in nature. So it's a stochastic viscous flow that they're observing. And then you have time scales. One time scale basically being the rate at which, the time it takes for it to lose its momentum. That I impart some momentum, how quickly does it lose that particular momentum, which is the relaxation time scale. You can have a time scale based on the Kolmogorov eddy, and you can have a time scale based on the time it takes for it to settle across a Kolmogorov eddy, which is what I was saying initially for the crystal problem, that how rapidly does it fall down. So which will give you then a Stokes number that is going to tell us how important is the role of particle inertia with respect to the time scale, the Kolmogorov time scale. You can get a settling parameter, which tells us how rapidly do you fall with respect to the velocity of the Kolmogorov eddy. So the Stokes number is typically not very large, and the settling parameter, or this number SV, can be quite significant. So now if you want to solve this in a turbulence problem without interaction was something that appeared as, I believe, the second paper in the first issue of JFM. The Safman-Turner's paper is something which precisely looked at this problem. No interaction involved. There are two particles which are sampling a turbulent velocity gradient, and based on the Gaussian statistics of the velocity gradient, they calculated the collision rate. So that's the Safman-Turner calculation. So we went about asking that, is there a way to improve this calculation, accounting for interaction and also accounting for the fact that the velocity gradient is not necessarily Gaussian in nature. So there are non-Gaussian statistics for the velocity gradient. Can that be incorporated? So once again, revisiting that equation I said earlier, that which is the relative velocity of the two spheres is now driven by turbulence, which is the first term. And the other term is the settling term, the relative difference in the weight. And both of these have multiplied this parameter M and N, which are the interaction terms. If there was no interaction, M and N would be just unity. There would just be driven by the flow and the difference in their weight. So the stochastic, yes. Mm-hmm.
How do you when you have a collision at some level of
Yeah, so you are saying that because the Reynolds number at the scale of the particle is so small that as the particle, so imagine that, one particle is held fixed for simplicity and the other is moving around. So the thing that you are trying to find is the resistance that I experience as I move. So what is the resistance to motion between the particle which is present there and I am as I'm trying to move from here? Now I try to find what is the resistance at the next location. Right. Now, these two are calculations done in these two configurations. Now, your question is, as I do this motion, during this motion, that's not equivalent to me finding the resistance in this location and finding in this location. That's the unsteadiness, right? Absolutely right. That becomes important if the Reynolds number becomes significant. So you will have the unsteadiness because you are solving a quasi-steady equation. The trajectories are obviously functions of time. But the underlying equations that you're solving to find the thing that is driving the interaction physics are the Stokes equation. So you have dropped the unsteady part there. Yeah. So Reynolds times Truhal is basically what is multiplying the unsteady part. So correct.
Circumstantially, when you're actually
right. So so the question is, what are the timescales that would be driving this aspect? So if I say there is a shear rate which is driving it, so I'll be constructing a Reynolds number. There is no inherent. So if I'm trying to measure what is the acceleration as I'm moving across, I'm not accounting for acceleration. So if I try to compute what is du dt as I move across, that du dt will still scale with some order one factor times the Reynolds number. If I had an unsteadiness where, let's say, there was an implicit, say for instance, a turbulence problem. There's a time scale over which the flow is also getting correlated or decorrelated. So if I have that time scale additionally appearing, I can have unsteadiness that becomes important. See, finally, what is important is Reynolds times Truhal, as you said. So that's the term which matters whether you have the unsteady inertia important in the problem. So even though you will have a du dt, you can calculate a du dt, that du dt is still being driven by an order 1 shear rate that is in the problem. So du dt will only scale with quantities that are order 1. So the Struhal is going to be an order 1 quantity if you calculate here, but it is still multiplied by an extremely small Reynolds number.
Isn't it also connected to how far close they are to each other? And as they come closer and closer, things are going to change very quickly.
Yeah, so you...
There should be a deceleration or acceleration just because they're near. That's what you're asking. So like there should be a Struhal number which...
So you are going to have a relative velocity that is basically being driven by whatever the forces that you have in the problem. So let's say there are two surfaces which are being brought very close to each other. So now the question is that I have, if I am calculating what is the amount of acceleration that is there in the fluid that is basically being driven as two surfaces are getting closer and closer, the Reynolds number is now becoming even small. It's not determined by the size. So even though the gap is getting small, the velocities are getting smaller, right? Because the relative velocity of separation is going with the separation. So if you say that u goes with the separation, and I try to find out what will be du dt of that particular quantity, that quantity is also a decreasing quantity. And now the Reynolds number that I should be thinking of should not be the sphere size Reynolds number. I should be thinking of a gap Reynolds number, which is getting even smaller because it is now the Reynolds number of the particle multiplied by like a lubrication parameter, like h by a. So the motion, as long as you are, you don't have an implicit very high frequency feature in the problem. So let's say whatever I said here, if you were to do this in an unsteady shear flow, that's an example. So you do this in an unsteady shear flow and you ask the question that there is a time scale over which, so it's oscillating problem. Should we do this or should we do it with the Struhal there? Now there you have a way to, tune how large is the unsteady part. And yes, it can play a role in those cases. When you are studying the interaction problem, if the flow was very rapidly fluctuating, then I can have, even though Reynolds is not large, Reynolds times Struhal can become quite significant, and you have to study the interaction in such a scenario. In the laminar problem, it is never a question. In the turbulence problem, you have to think a little bit in terms of whether the time scale associated with the turbulence, how the turbulence changes, would bring in an inherently an unsteady inertia in the calculation. But if you do a shear flow with oscillation, you're absolutely right. You do need to think about whether you can get away doing this interaction calculation, assuming a quasi-steady approximation.
All of these arguments are based on background.
Correct.
Why do those numbers become important? If the particle is disturbing the flow, right?
That is accounted for, right? So the fact is, see this, if the particle was, let's look at this maybe. Yeah, so if the particle was in a linear flow and there was no interaction, they were not disturbing the flow, then the relative velocity is just driven by the first term on the right hand side, which means that I'm two tracers which are moving towards each other. They are doing nothing to the flow. Because these are spheres of finite size and they are moving and creating a disturbance, and disturbance not just by the virtue of their motion, but also by the virtue of the neighbor's motion, that is going to create a feedback. So all of this I've put together here and said what is the relative velocity of separation. I've not said anything about what is the flow field that is used to arrive at this. So if you were to actually look at the velocity field for this problem, it is not the background flow. It is the background flow plus a disturbance. And the disturbance is actually as important as the background flow, or even more important than the background flow in the neighborhood of the particle, because it has to satisfy the no-slip boundary condition. So it can't be the background flow. Far away, it is the background flow. But if you were to just because here we are asking questions of rate of collisions. We are not, looking at what the flow field looks like. So the flow field, this is actually not a very good picture, but the flow field here, if this, it's going to have a slight bump here. There will be like a slight deviation when it comes here. This is supposed to be also actual one. I've just drawn it lazily with the exact same curve, but it should be like a slight bump that it would be there. Let me see if I had it. Yeah, probably it's. Yeah, so there is going to be a bump for the flow. I'm showing the trajectories, but because it's a quasi-steady problem, what you are solving for is an equation that is steady in a sense of the trajectories. The particle pair trajectories and the streamlines will be identical. Amma, you should tell me when should I stop. I'm probably gone.
Like how about in a few minutes from now?
Sure. So I will just wrap with the.
It's all like mainly my fault because I can't move ahead so easily.
No. So fine. I will just end with this part and give some reflections on things ahead. So you can do the same thing that you tried out for the laminar flow now with the turbulent flow, provided you have a way of getting the velocity gradient. So there are different ways of doing it. You can obviously take the velocity gradient from DNS. You can take the velocity gradient, making some assumptions about the velocity gradient. One assumption you can say that the velocity gradients are Gaussian fields. And let's say I have Gaussian fields and then I use that Gaussian field to solve for the problem. Or you use some synthetic velocity gradient model, like the kind that I said, done by Grimagi and Pope. It's a Lagrangian velocity gradient model. Does some nice things in terms when you are interested in these kind of problems. So that's the back end of how you get the velocity gradient. And so we do these calculations of finding the collision rate with the presence of background settling and the computation of turbulence. So we can do this in two scenarios. So we did this one, which was assuming that the particles are sampling the velocity gradient as per the Lagrangian fluid trajectories, which is not a good assumption because the particles are sampling velocity gradient along settling trajectories. So the velocity gradient should not be sampled along a fluid trajectory. But if you do that, which means settling is very weak, you can calculate the collision rate. And this is a comparison with experiments done in. So because you have to ask, how do you compare these things with experiments? Precise collision calculations, there are some studies that are coming up now, but you do indirect comparisons. Indirect comparisons as in like if you have a spray, which is now colliding and growing in size, you have the growth of the distribution. And from the growth of the distribution, you try to infer what would have been the rate of growth. So that's what has been done here. You have tried to compute the rate of growth. And these circles are what we have from the theoretical calculation, and the crosses are what you have from the experiments. The colors are different RE lambda. So you have like two different values of RE lambda, and that's one of the comparisons which we could do with the calculation of collision efficiency. So I'm just going to quickly summarize that this is what the building blocks actually are. So we have been looking at various kinds of physics incorporated in this collision rate. But the interesting part is why and how do we use this? So far everything that I've said is how do you do this detailed collision calculation? Once you get the collision rate, maybe you can take it forward and get the droplets as distribution, but how does it matter? How does it actually do anything in terms of relevance in terms of the picture that I had of these droplets growing in size? So this is one such work done by Pinsky and Kane in 2007, where they started with a distribution. The distribution is on the left side, the peaky triangular one that you see. And they played with two parameters. One is the number of drops that are there initially, the number density, and the other is the turbulence intensity. So as you move along and you see the bottom ones are the ones where the turbulence intensity, it's not very easy to read, but 1000 centimeters square per second cube is the bottom right one. And the top one on the left is 100 centimeters square. So the turbulence intensity is actually increasing if you move in the diagonal. So there is a dramatic difference that you see is that the increase in turbulence is giving you a significantly broader distribution and towards very large drops. So if you were, and this is a simulation done by solving that Boltzmann-like equation. So you feed in a collision kernel, solve the Boltzmann-like equation, and within 30 minutes, so this is like t equal to 0 was the initial PQ1, and at 30 minutes, you look at what the broad spectrum is. So you kind of are trying to go towards making real-time predictions of whether you are going to get very large raindrops that are going to suddenly burst out into an immediate rain that can happen. And there are different places around here where you can get these information. So near Tirupati, you have this facility maintained by National Atmospheric Research Lab, NARL. This is a whole array of radar. Like, it's a huge facility. I mean, even if you don't have any interest in this area, just for the amazing setup they have, it's worth a visit. They have this amazing facility of ground-based radar, which can give you data of turbulent intensity, the distributions of droplets that are there. So they have a very nice facility which can be used in order to find this kind of ground-based measurements. And I think just a week back, you had the launch of the latest INSAT satellite, which is because so far the satellites that we have had, they were mostly focused on getting the information from the cloud top. So the cloud top information is not like a very good information to find what is the distribution that is inside and subsequently making prediction. So this is the INSAT 3DS, which is going to give a more detailed height-wise information of what the droplet sizes are. So these are ways by which it can be connected and done in some sense where you can have information from observations, either ground-based or satellite-based, which can then be used in order to make some real-time predictions regarding the droplet size distribution. And I mean, I spoke only about particle interactions being spheres. These are simulations are borrowed from Harshit for spheroids. So, I mean, these are like what would happen when you have ice crystals when they are interacting. So these are significantly challenging computationally. Whatever I said, they are exploiting the symmetry of spheres. So the moment you go for something more realistic, you can't do anything of that sort. Just to wind up, I found this is something I came across recently. I wasn't aware of this until now. So Joanne Simpson is the first woman who received a PhD in meteorology, if not in the world, definitely in the US. And she has done phenomenal amount of work on clouds. And what you see on the top are pictures she drew by hand looking at the clouds. And again, like within a span of few minutes. And it's worth seeing the details that she was trying to capture, saying what are the features that are universal and what are the features that are probably evolving very quickly to the turbulence. So what features are preserved in the turbulent flow and what features was not around. And that's how she went about observing clouds. And that's basically, I mean, an immense amount of work that she has done on this. This is, I think, clouds that she was observing near Nantucket in the Cape Cod area of Massachusetts. And this is something which I came across again recently from Bhatt's article in Resonance on Clouds, a diary from RN's, one of pages from RN's diary where he was making notes. This is now what, 60 years back. So he was making notes, time-wise cataloging, I think the Kempegowda Tower, what he was observing regarding the clouds. And very nice way in which, I mean, you're trying to actually see, because it's so visual, you're trying to see and make notes of what you are seeing. And we have gone from there and we have come to now people making in the bottom what is called as a global cloud climatology, that what is the distribution of clouds in latitude and longitude, that kind of detail we have gone to. And in the top is, this is I think called CloudNet. It's a agglomeration of facilities from Europe, but this is a measurement done in, I think something they have in Barbados. Height is obviously one axis, the other is time, and the colors are what is there in the cloud. So you obviously see that you have blue are droplets, then yellow is ice, melting ice, aerosol, and then eventually they even have insects. So it's like profiling all the way till what at different heights do you have. So that's the kind of detail that has gone from how people started looking into clouds around 80 years back to where we are now. And there is still, I think, room for a lot more to be done. So sorry for taking extra time. So thank you so much for your time.
Maybe we'll save future questions for over lunch.
Yeah, sure.
Great stuff.
Thank you.